Real zeros of polynomials. In the last section, we saw how to determine if a real number was a zero of a polynomial. In this section, we will learn how to find good candidates to test using synthetic division. In the days before graphing technology was commonplace, mathematicians discovered a lot of clever tricks for determining the likely locations of zeros. Technology has provided a much simpler approach to narrow down potential candidates, but it is not always sufficient by itself. For example, the function shown to the right does not have any clear intercepts. There are two results that can help us identify where the zeros of a polynomial are. The first gives us an interval on which all the real zeros of a polynomial can be found. Cauchy's bound. Given a polynomial, f of x equals a sub n x to the n power plus a sub n minus y x to the n minus 1 power, and so on, plus a sub 1 x plus a sub 0. Let m be the largest of the coefficients in the absolute value. Then all the real zeros of f of x lie in the interval negative m divided by absolute value of a sub m minus 1, m divided by a absolute value of a sub m plus 1. Example 1. Let f of x equals 2x to the fourth power plus 4x cubed minus x squared minus 6x minus 3. Determine an interval which contains all the real zeros of f. To find the m from Cauchy's bound, we take the absolute value of the coefficients and pick the largest, in this case, absolute value of negative 6 equals 6. Divide this by the absolute value of the leading coefficient 2 to get 3. All the real zeros of f lie in the interval negative 6 divided by absolute value of 2 minus 1, negative 6 divided by absolute value of 2 plus 1 equals negative 3 minus 1, 3 plus 1 equals negative 4, 4. Knowing this bound can be very helpful when using a graphing calculator, since we can use it to set the display bounds. This helps avoid missing a zero because it is graphed outside of the viewing window. Try it now. Determine an interval which contains all the real zeros of f of x equals 3x cubed minus 12x squared plus 6x minus 8. Now that we know where we can find the real zeros, we still need a list of possible real zeros. The rational roots theorem provides us a list of potential integer and rational zeros. Rational roots theorem. Given a polynomial, f of x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power plus and so on, plus a sub 1 x plus a sub 0 with integer coefficients, if r is a rational zero of f, then r is of the form r equals plus or minus p divided by q, where p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. This gives us a list of numbers to try in our synthetic division, which is a nicer place to start than simply guessing. If none of the numbers in the list are zeros, then either the polynomial has no real zeros at all, or all the real zeros are irrational numbers. Example 2. Let f of x equals 2x to the fourth power plus 4x cubed minus x squared minus 6x minus 3. Use the rational roots theorem to list all the possible rational zeros of f of x. To generate a complete list of rational zeros, we need to take each of the factors of the constant term a sub 0 equals negative 3 and then divide them by each of the factors of the leading coefficient a sub 4 equals 2. The factors of negative 3 are plus or minus 1 and plus or minus 3. Since the rational roots theorem tacks on a plus or minus anyways, for the moment, we consider only the positive factors 1 and 3. The factors of 2 are 1 and 2, so the rational root theorem gives the list plus or minus 1 divided by 1, plus or minus half, plus or minus 3 over 1, plus or minus 3 halves, or plus or minus 1, plus or minus half, plus or minus 3, plus or minus 3 halves. Now we can use synthetic division to test these possible zeros. To narrow the list first, we could use graphing technology to help us identify some good possibilities. Example 3. Find the horizontal intercepts of f of x equals 2x to the fourth power plus 4x cubed minus x squared minus 6x minus 3. From example 1, we know that the real zeros lie in the interval -4, 4. Using a graphing calculator, we could set the window accordingly and get the graph below. In example 2, we learned that any rational zero must be on the list plus or minus 1, plus or minus half, plus or minus 3, plus or minus 3 halves. From the graph, it looks like -1 is a good possibility, so we tried that using synthetic division. Success. Remembering that f was a fourth degree polynomial, we know that our quotient is a third degree polynomial. If we can do one more successful division, we will have knocked the quotient down to a quadratic, and if all else fails, we can use the quadratic formula to find the last two zeros. Since there seems to be no other rational zeros to try, we continue with -1. Also, the shape of the crossing at x equals -1 leads us to wonder if the zero x equals -1 has multiplicity 3. Success again. Our quotient polynomial is now 2x squared minus 3. Setting this to 0 gives 2x squared minus 3 equals 0, giving x equals plus or minus square root of 3 halves equals plus or minus square root of 6 divided by 2. Since a fourth degree polynomial can have at most 4 zeros, including multiplicities, then the intercept x equals -1 must only have multiplicity 2, which we have found through division, and not 3 as we had guessed. It is interesting to note that we could greatly improve on the graph of y equals f of x in the previous example given to us by the calculator. For instance, from our determination of the zeros of f and their multiplicities, we know the graph crosses at x equals negative square root of 6 divided by 2, which is approximately -1.22, then turns back upwards to touch the x-axis at x equals -1. This tells us that despite what the calculator showed us the first time, there is a relative maximum occurring at x equals -1 and not a flattened crossing as we originally believed. After resizing the window, we see not only the relative maximum, but also a relative minimum just to the left of x equals -1. In this case, mathematics helped reveal something that was hidden in the initial graph. Example 4. Find the real zeros of f of x equals 4x cubed minus 10x squared minus 2x plus 2. Cauchy's bound tells us that the real zeros lie in the interval -10 divided by absolute value of 4 minus 1, -10 divided by absolute value of 4 plus 1 equals -3.5, 3.5. Graphing on this interval reveals no clear integer zeros. Turning to the rational roots theorem, we need to take each of the factors of the constant term a sub 0 equals 2 and divide them by each of the factors of the leading coefficient a sub 3 equals 4. The factors of 2 are 1 and 2. The factors of 4 are 1, 2, and 4, so the rational roots theorem gives the list plus and minus 1 over 1, plus and minus half, plus and minus 1/4, plus and minus 2 over 1, plus and minus 2 over 2, plus and minus 2 over 4, or plus or minus 1, plus or minus half, plus or minus 1/4, plus or minus 2. The two most likely candidates are plus and minus half. Trying half, the remainder theorem, the remainder is not 0, so this is not a 0. Trying negative half, success. This tells us 4x cubed minus 10x squared minus 2x plus 2 equals x plus half multiplied by 4x squared minus 12x plus 4, and that the graph has a horizontal intercept at x equals negative half. To find the remaining two intercepts, we can use the quadratic equation, setting 4x squared minus 12x plus 4 equals 0. First, we might pull out the common factor, 4 multiplied by x squared minus 3x plus 1 equals 0. X equals 3 plus or minus the square root of 5 divided by 2, which is approximately 2.618.